Alright folks, so let's look into the solution here. I have a long integer x, which I declare here, and which I just input here, okay? So x will be the integer that we will be checking to see if it is a prime or not. So here I have the main for loop. So in this main for loop, we begin from number 3 up until the square root, and we check to see if we can find a divisor for our number. So here I'm using integer I initialize it to be equal to 3, okay? And as long as I times I, so multiplied by itself, is less than or equal to x, I will be checking to see if I is a divisor. And I increment by 2 every time, because for the even numbers, we're gonna have a special case, which we will check afterwards, so after the main for loop. So we don't need to check any other even number, because if an even number divides x, then for sure number 2 divides x as well, okay? That's pretty obvious. And we just say x modulo I, so the remainder of the integer division of x by I, if that's equal to 0, then I divides x, and thus x is not a prime. So we output not prime, and we return. And now on to the corner case, which I mentioned. So here we have an if statement, which has the OR operator here. So 2 cases which can make this if statement true. The first case is when x divided by 2 gives a remainder of 0. So x modulo 2 equals 0. And thus x is an even number. And x is not equal to 2. Because if x is equal to 2, then we have a prime number essentially, okay? So this value is true for even numbers that are not equal to 2 essentially. For those cases, we just output not prime and we return. And the other case that we do the same is when x equals to 1, okay? Because with the main for loop, if x equals to 1, we're not gonna report that it is not a prime, okay? Because we're essentially not even gonna iterate once in this for loop, because 3 times 3 equals to 9, which is for sure greater than 1, okay? So now that we're done with the corner cases as well, if we have reached this point here, the 23rd line, then for sure we have a prime number essentially, okay? Again, why do I check only up until the square root in the main for loop? Is because if we have reached the square root and we haven't found a factor of x, so a divisor of x, then we're not gonna find a divisor in the future, because if that divisor exists, then it is multiplied with a number which is less than the square root of x, okay? Because any number greater than the square root multiplied by that number, it will give me a result which is greater than x. So there is no reason to check beyond the square root, okay? So that's pretty much the solution. Let's go ahead and test this real quick. Let's do a quick test. So here I'm just gonna compile prime number check, and I'm just gonna run the default name. So 1, 2, 3 is not a prime, 2 is a prime, 3 is a prime. Let's clear this. Let's check 171. Is this a prime? No. Let's check 73. It's a prime, and let's check 13. So it's a prime, yes. So that's pretty much the solution. For those that are wondering, how is primality check done for the RSA, for example? Okay, I'm taking RSA. There are a lot of algorithms who need to execute primality tests. Okay, but the reality is that when you need to check for to primality check a very big number, this solution that I am offering here, which is essentially a linear solution, okay, will not suffice. That's because you don't have the time to go up until the square root of a very big number to check all of the numbers to see if they are divisors, if they divide our number or not. So what you do in these cases, for example in RSA, is you take the first 100 primes or the first 1000 primes, it depends on the implementation really, and you check if these primes divide our randomly generated number. If these numbers do not divide our randomly generated number, then you can calculate a confidence level, which is like, for example, this random number is not divided by any of the first 100 primes. So we have a confidence level of 99.999%. That's just an example that I made up. Chance that it is a prime number. So you use these approximation methods for very big numbers, okay? And if you are 99.9999% sure that it is a prime number, then you have to be extremely unlucky that it is not, okay? Of course, like these primality checks need more elaborate math to understand how they work. You have to study number theory, some extra number theory to understand how these primality checks work. But for these, for numbers that are that fit into this data type, the long integer data type, we can have linear solutions. Yes. So these numbers go up until 2 to the power of 64 minus 1, because we need one more bit for the sign, essentially. For the assigned long version, we can go up to 2 to the power of 64, right? Or yeah, 2 to the power of 65 minus 1, because in that case we're gonna have all aces, 64 bits, all of them set to 1. Then you have 2 to the power of 65 minus 1. Okay, so that's the greatest number you can have in a data type here. But anyways, that's it for the video. So for numbers that fit into the data type, remember you can use this solution which I showcase here. If you're gonna execute primality tests for a lot of numbers, it's more beneficial to calculate the prime numbers up until a certain number and check if those prime numbers divide, like only check about these prime numbers, because you don't need to do this. You don't need to linearly go through every number to check, okay? You can use just the prime numbers. How you can calculate these prime numbers fast up until a certain number, I have already made a video. I'm gonna put this in the description, so you can look at that video as well. And essentially you can have the sieve that generates those primes, and just check the prime numbers directly instead of having this for loop here, which goes through the numbers one by one. Okay, so that's pretty much it for the video. I hope this video helped you understand how to check if a number is a prime, and subscribe to the channel, like the video, and I will see you in the next one. Goodbye.